Hello everyone. Now I am going to tell the topic of wavelet packets. If we want control over the partitioning of the time frequency plane, the FWT must be generalized to yield a more flexible decomposition called a wavelet packet. The most of this generalization is an increase in computational complexity from big O of capital M for the FWT to big O of capital M log M. The fast wavelet transform decomposes a function into a series of logarithmically related frequency bands. The structure of the tree and links the appropriate FWT scaling and wavelet coefficients to its nodes. Now let us see the coefficient tree. W suffix y of capital J comma n is equal to function of n. They are subscale of W suffix y j minus 1 comma n and W suffix xi j minus 1 comma n, and these are subsquare of W suffix y j minus 2 comma n and W suffix xi j minus 2 comma n. Now let us see the analysis tree for the two scale FWT analysis back. Capital V suffix j subscale of capital V j minus 1 and capital W j minus 1. Capital V j minus 1 subscale of capital V j minus 2 and capital W j minus 2. The root node is assigned the highest scale approximation coefficient, which are samples of the function itself, while the leaves inherit the transforms approximation and detailed coefficients output. The lone intermediate node W suffix pi capital J minus 1 comma n is a filter bank approximation that is ultimately filtered to become two leaf nodes. The coefficients of each node are the weights of a linear expansion that produces a band-limited piece of root node. Any such piece is an element of a known scaling or wavelet subspace. Although the variable is used to denote both coefficients and subspaces, the two quantities are distinguishable by the format of their subscripts. These concepts are further illustrated where a three-scale FWT analysis bank analysis tree and corresponding frequency spectrum are depicted. Now let us see a three-scale FWT filter bank. Function f of x belongs to capital V of j that are subdivided into h suffix xi of minus n that goes on to 2 decimation gives rise to capital W of suffix j minus 1, and h of pi into minus n goes on second decimation gives rise to capital V of j minus 1. Likewise, it goes on the FWT filter bank that gives capital W suffix j minus 3 and capital V suffix j minus 3. Now let us see the decomposition space tree. Capital V suffix j that are subscale of capital V suffix j minus 1, capital W suffix j minus 1. Now capital V suffix j minus 1 gives two subdividends, that is capital V j minus 2, capital W j minus 2. That capital V suffix j minus 2 that are subdivided into capital V suffix j minus 3, capital W suffix j minus 3. And now let us see the spectrum splitting characteristics. Now in the horizontal axis, angular frequency that from 0 to pi, where vertical axis that is magnitude of amplitude frequency that gives rise to spectrum splitting characteristics. The three-scale analysis tree from the above figure for example makes the possible the following three expansion operations. That is, capital V suffix j is equal to capital V suffix j minus 1, capital W j minus 1, and capital V suffix j is equal to capital V suffix j minus 2, capital W suffix j minus 2, capital W suffix j minus 1, and capital V suffix j is equal to capital V suffix j minus 3, capital W suffix j minus 3, capital W suffix j minus 2, and capital W suffix j minus 1. They correspond to the 1, 2, and 3 scale FWT decompositions. They may be obtained by letting J naught is equal to capital J minus capital P for P is equal to 1, 2, 3. In a general, a P-square FWT analysis tree supports P unique decompositions. Analysis trees are also an efficient mechanism for representing wavelet packets, which are more than conventional wavelets transforms in which the details are iteratively filtered. Thus, the three-scale FWT analysis tree to become the three-scale wavelet packets tree shown as. Now, see the three-scale wavelet packets analysis tree. Capital V suffix j subdivided into capital V suffix j minus 1, capital W suffix j minus 1. They are subdivided into capital V suffix j minus 2, capital W suffix j minus 2, and capital W suffix j minus 1 subdivided into capital W suffix j minus 1, comma A, capital W suffix j minus 1, capital D. Likewise, they are subdivided into 2 to 3 scale wavelet packet analysis. Now let us see the filter bank and spectrum splitting characteristics of 3-scale full wavelet packet analysis tree. Now we see the 3-scale filtering bank. F of x belongs to V of j, that h of xi of minus n 2 decimation gives rise to capital W suffix j minus 1. They are subdivided into 2, and the R goes on, they subdivided into two parts until they reach W suffix j minus 1 comma dd, W suffix j minus 1 comma da, W suffix j minus 1 ad, W suffix j minus 1 aa. Now h of phi of minus n 2 decimation gives rise to V of suffix j minus 1. That R goes on to two steps, and finally they gives W suffix j minus 2 comma d, W suffix j minus 2 comma a, W suffix j comma 3, W suffix j minus 3, V of j minus 3. The below spectrum splitting characteristics show the three-scale full wavelet packet analysis tree, that are horizontal axis which is angular frequency and vertical axis which is amplitude of h of omega. For the instance, Vj can be expanded as capital V suffix j is equal to capital V suffix j minus 3, W suffix j minus 3, W suffix j minus 2 comma a, W suffix j minus 2 comma d, W suffix j minus 1 comma a, W suffix j minus 1 comma ad, W suffix j minus 1 comma da, W suffix j comma dd, whose spectrum is just shown as the decomposition of the wavelet packets, which is capital V suffix j is equal to capital V suffix j minus 1, capital W suffix j minus 1 comma a, capital W suffix j minus 1 comma da, W suffix j minus 1 comma dd. This shows the spectrum of the decomposition which the wavelet packets that can expanded in the 3-scale wavelet packets. In general, P-square one-dimensional wavelet packet transforms a associated analysis tree that supports d of p plus 1 is equal to d of p whole square plus 1, which in decompositions where d of 1 is equal to 1, which is that large number of valid expansions. The packet based transforms provide improved control over partitioning the spectrum of the decomposed function. The cost of this control is an increase in computational complexity. The first decomposition of two-dimensional FWT is the spectrum or the subspace analysis tree. This shows the first decomposition of the two-dimensional abnormal tree, which shows the horizontal axis which is angular frequency and vertical axis which is shows the omega from pi to minus pi. In horizontal axis we shows the minus pi to pi, which shows dvd h dvd, which shows the spectrum and the variations that occur from the minus pi to pi. Now, the three-scale full wavelet packet decomposition tree that shows in three ways, which is the subdivided into three parts, which gives the subdivision of three parts, and that makes the last that gives the four wavelet packets. Therefore, a single wavelet packet tree presents numerous decomposition options. In fact, the number of possible decomposition is often so large that it is impractical, if not impossible, to enumerate or extreme them individually. An efficient algorithm for finding optimal decompositions with respect to application specific criteria is highly desirable. As well be soon, classically entropy and energy based cost functions are applicable in many situations and are well suited for use in binary and quaternary tree searching algorithms. Now let us see the example of compressing fingerprint image. In first image we see the scanned fingerprint. In second image we see the 3-scale full wavelet packet decomposition. By using 3-scale wavelet packet trees, there are 83,522 potential decomposition that could serve as a starting point for the compression process. In figure 2 shows one of them full wavelet packet which has 64 leaf decompositions like the analysis tree. That leaves of the tree compressed to the subbrands of 828 array of the decomposed subimages in image B. One reasonable criterion for selecting a decomposition for compression of the image is the additive cost function, which is capital U of f is equal to xi of m comma n mod f of m comma n. Entropy is near zero indicates function with little to no. For each node of the analysis tree, beginning with the root and proceeding level by level to the leaves. Now let us see the step 1. Compute both the energy of the nodes denoted EP. VP is parent energy and the energy of its four offsprings denoted EA, EH, EV, ED, and for two-dimensional wavelet packet decompositions, the parent is a two-dimensional array of approximation or detail coefficients. The offspring are the filtered approximation, horizontal, vertical, and diagonal details. In step 2, if the combined energy of the offspring is less than the energy of the parent, that is EA plus EH plus EV plus ED less than EP, include the offspring in the analysis tree. If the combined energy of the offspring is greater than or equal to that of the parent, prune the offspring, keeping only the parent. It is a leaf of the optimized analysis tree. Now, in the figure, an optimal wavelet packet decomposition for the fingerprint, which shows in the above figure. In below figure, which shows the diagram of the optimal wavelet packet analysis tree for the decomposition. Now let us see the biorthogonal Cohen dive, which is via filter coefficients, which is shown in the tabular form. The coefficients of biorthogonal filter synthesis can also be computed. There are cross-modulated versions of decomposition filters. Now, this figure shows that the member of Cohen Dovich Fayuya biorthogonal wavelet family, which first two figures shows that the decomposition filter coefficients and next two filters shows that the reconstruction filter coefficients and next two shows the dual wavelet and scaling function and this shows the biorthogonal wavelet family. Thank you.